So you followed me on getting to the monomers. That's the hard part, getting the monomers. Step 2 is we got to polymerize them. We have to build big, long chains of these monomers. And that's what we're talking about here, how you form nucleic acids and polypeptides. It's called polymer synthesis. You have to combine them together. Do you guys remember what it is called, what kind of reaction it is, where you take two molecules and you combine them together? You build something new. You synthesize something new. It's from Bio 101, so I wouldn't expect you to necessarily remember. It's called dehydration synthesis or condensation reaction. Do you guys remember those at all? Oh yeah, now you're nodding. Or not. Don't worry. We have a big problem with water. So you've got to build molecules using dehydration reactions. That means they exclude water. You build molecules, then that requires energy. Breaking molecules releases energy. The process we're going to use to break molecules is called hydrolysis. In our current position with this process, we do not want hydrolysis to occur. It slows down polymerization. It's almost like, any of you guys have a little brother or sister? Okay, do you remember when you were younger and how you would be trying to do something and they would follow right behind you and destroy it because they suck? Yeah, okay, cool. That's what's happening with condensation reactions and polymerization. Basically, if you've got a condensation reaction happening in water, these molecules are being built. As long as you're in water, hydrolysis is going to keep happening. You keep breaking these molecules faster than you can build them. And our prebiotic soup, like most soup, is made primarily of water. It's an aqueous solution. So as much as you're having condensation reactions, you're also having hydrolysis reactions. Nothing's getting built. In your body, how are these long molecules built? What mediates almost all the reactions in your body? What makes them happen faster? So in your body, you've got these... Yeah, thanks, enzymes. Enzymes are catalysts. They speed up reactions by millions of times. Earliest history, no enzymes. Basically, it's all happening due to sheer either chance or the conditions are just right to allow condensation to happen faster than hydrolysis. So here's where we get some different hypotheses. One is called the imbued clay hypothesis. Clay is kind of an important substrate. There's a hypothesis that a pool of prebiotic soup laying on clay could evaporate sufficiently to allow polymerization to exceed hydrolysis. Let me draw that out for you. Have you guys ever been to the beach? Okay, bear with me on this. If you've been to the beach, right along the shoreline, when the wave washes up, what happens to any water that's left behind? It gets foamy, yeah, but what happens to the water washes up and then it goes back, and let's say you're in a little dip. What happens to the water in that dip that you're standing in? Say it again. It sinks straight down, right? It retreats back to the normal level of the water. So here we've got clay. If a wave washes up on shore, the water will get filtered through the clay. But the minerals dissolved in the water may not. The clay can bind the minerals in water. And in fact, it binds amino acids and it binds nucleotides. Clay has a slightly positive charge to it, and I'm pretty sure it's a slightly positive charge, and DNA has nucleotides have a slightly negative charge. So it holds on to those as water goes through it. That's kind of cool in itself. So what you're doing is you're creating a dry area, so there's no water here, with a whole bunch of nucleotides and amino acids. It's here where that can occur. Oh, and clay also attracts metal cations, and metal cations act as catalysts. They're not like as efficient as enzymes, but they do speed up reaction rates to combine polymers. So boom, if we got clay, we can have reactions. We can have polymers forming. That's the first hypothesis. It's totally reasonable. It totally works. But turns out in 2004, we found another hypothesis that also works. It showed that it's possible for polymers to form in an aqueous solution, so in water. overcoming hydrolysis if carbonyl sulfide is present. So if you have this molecule carbonyl sulfide, it doesn't matter if water's there, you can still build polymers. Hydrolysis just won't happen. And nobody cares is going to the big reveal. Where do you think carbonyl sulfide is present? Deep sea vents. That's exactly where it's present. So at the bottom of the ocean, at those geothermal vents where we just a second ago, in the last lecture, said we are producing monomers, that we also have carbonyl sulfide, which allows those monomers to form polymers. Right here at the bottom of the ocean, we could have had the formation of not just monomers, but polymers as well. So there we go. Step 2, form the polymers. We've got to overcome the force of hydrolysis. We've got to build faster than we break. And in order to do that, we could either use clay, which will bind cations, exclude water, and allow for the polymers to be built, or we could have this happen at the bottom of the sea, at the geothermal vents with carbonyl sulfide, pushing water away, allowing the reaction to occur. Either way works, but now we've gone from having just monomers to now we have polymers.